So for this example, we want to find the indefinite integral of pi sine of pi x dx. And we need to check to see, since our function sine has something other than x in it, we need to check on that composite rule. So inside the sine, we're going to consider that to be our g. That's pi x. The derivative of pi x is pi. And so this does fit the pattern of that composite rule. And so we will be able to find the antiderivative of this with the composite rule. So let me remind you that composite rule looks like this. You have the indefinite integral of f of g of x, g prime of x, dx. And the antiderivative of that will be big F. Big F is the antiderivative of f. And we have that inside function being the same and plus our constant. So that's what I was looking for in this example. I was looking for the inside function and the derivative of the inside function before I was able to apply this antiderivative rule. So in order to apply this rule, I need the antiderivative of f, which is our outside function. So this sine right here would be our outside function. So we need the antiderivative of sine, which is negative cosine. We're going to leave the inside alone and add our arbitrary constant. So we have the integral of pi sine pi x being negative cosine pi x plus c. For this question, we want to evaluate the indefinite integral. We have the antiderivative or integral of cosine 5x dx. Let's write that out. We've got the integral of cosine 5x dx. So inside of the cosine, I have 5x. I'm going to think of that as u. And in order to evaluate this integral, I also need to have the derivative of u. The derivative of u, so if u is equal to 5x, the derivative of u prime, is 5. So I'm missing that 5 multiplied by the cosine of 5x in this question. So what I would do is I would multiply by 5 over 5, bring in the 5 that I need, so now we have 1/5 the integral of 5 cosine of 5x dx. And now I have this u as well as the u prime, and I can use the composite antiderivative pattern. Composite function pattern. And in that pattern, let me go ahead and write it out for you before we use it. It is the integral f of g of x, g prime of x dx. So your antiderivative needs to fit this pattern. And then the way you calculate the antiderivative is that you need to find the antiderivative of the outside function, so that we write as big F. We evaluate that big F at the inside function, which is g of x, and of course we want to add our constant. So in our example, our outside function of lowercase f is the cosine. So we need to find the antiderivative of cosine. So we're going to carry down that 1/5, that constant. The antiderivative of cosine is sine. We're going to leave that inside function alone and add our constant. So we have 1/5 sine of 5x plus c as our antiderivative. So for this question, we're going to evaluate the indefinite integral of cosine of 5x dx. And this time I'm going to do the problem with the substitution method. So usually you let something that is on the inside be what you're substituting for. So I'm going to let the inside be 5x. Sorry, I'm going to let inside be u, which is 5x. I'm going to calculate the derivative of that, which is du dx is 5. I'll rearrange, that's du equals 5 dx, and I'll divide by 5. And now I have dx equals du over 5. So now I have, for the inside, I'm going to substitute that u. And for the dx, I'm going to substitute du over 5. When I make that substitution, it becomes the integral of cosine u, and dx is du over 5. I'm going to factor out this 1/5 from the integral to write this as 1/5 the integral of cosine u du. And now I'm going to calculate the antiderivative on cosine. The antiderivative of cosine is sine. I carried down that 1/5 as a constant multiple, and I left the inside the same. Of course, we need our plus c as well. And then finally, we want to bring back our original variable. So our original variable was 5x. That's 1/5 sine of 5x plus c for our antiderivative of cosine 5x dx. Okay, so on this example, we want to find f prime of x, and f of x is given to us to be an integral, a definite integral from -3 to x of t squared plus 2t plus 3 dt. So when we're calculating the derivative of an integral, this is using the second fundamental theorem of calculus. And with the second fundamental theorem of calculus, from our textbook, it looks something like this. You're going to have the derivative with respect to x, the integral of from a to x of f of t dt, and this is equal to f of x. So what's going on here is that the derivative and the integral are inverse operations of each other. And so what happens is that they sort of cancel each other out. Okay, now I'm going to go into a little bit more detail about that before we do this problem. So I'm going to rewrite this one more time. We've got the derivative of the definite integral from a to x of f of t dt. And if we think about this using the definition of the first fundamental theorem of calculus. The first fundamental theorem of calculus says that we need to find the antiderivative of f, which is capital F, and then we evaluate that at the upper bound minus the lower bound. We still need to calculate the derivative to finish this off. So then when you're calculating the derivative, you would be doing f prime of x and f prime at a, well, no, that's not exactly right. This portion, f of a, has no variables in it. So you're taking the derivative of a constant, and the derivative of a constant will be 0. And so then you have f prime, capital F prime of x. Now, let's back up a second here. We said that we needed to calculate the antiderivative of lowercase f, and that's capital F, and then we calculated the derivative of that. And the derivative of that should be f. Derivative and antiderivative are opposite operations of each other. So that's how this works out, that the integral and the derivative end up canceling each other out. So for our example, if we use that idea of the second fundamental theorem of calculus, we are trying to calculate the derivative of an integral. So that means that when we calculate the derivative is going to cancel out this integral, but we need to evaluate at this upper bound. I get to ignore the lower bound. And the reason why I get to ignore the lower bound is because it's a constant, and the derivative of a constant is 0. So I need to evaluate this function at that upper bound, and that will give me x squared plus 2x plus 3 as my answer for the derivative of capital F. So that's using the fundamental theorem of calculus. Sorry, the second fundamental theorem of calculus. Thank you for checking out my videos. Have a great day.